Welcome to Deep Dive Lab, where we break down and dissect cutting-edge scientific research, from advanced biomedical technologies to breakthroughs in AI, material science, chemistry, and physics, all told as compelling, easy-to-follow stories.
And today's story is, well, it's definitely going to bend your reality a little bit.
Oh, absolutely. So I want you to just stop what you're doing for a second and imagine a pair of magical coins. You flip one right here on Earth, and an astronaut flips the exact same kind of coin on Mars.
Right, millions of miles away.
Exactly. And without any signal passing between them, without any possible way for them to, communicate,
Yeah.
they instantly land on the exact same side every single time.
Which is just wild.
Yeah. Heads here, heads on Mars, tails here, tails on Mars. Instantly.
It completely breaks the brain because, that defies literally everything we intuitively know about how the physical world operates.
Yeah, it really does.
It violates the basic rules of cause and effect that, you and I interact with every single day.
But today's deep dive is an exhaustive journey into exactly that phenomenon. We are doing a full literature survey into quantum entanglement.
And it is a huge topic.
It is. Our mission today is to trace how scientists actually proved this so-called spooky action is real, how they're actively using it right now to build unhackable internet networks, and, perhaps most mind-blowing of all, how it might literally hold the fabric of space-time itself together.
It's an incredible story. We're looking at a journey from what was once considered a massive philosophical headache to what is now the foundation of an entire technological revolution.
Right. But, to appreciate how far we've come, we kind of have to start with the original scientific mystery, because for a long time, physicists were incredibly skeptical of this idea.
Oh, massively skeptical. Einstein famously hated it.
Right. The idea that two particles could just instantly coordinate their behavior across vast distances. And honestly, let's be real, you can't really blame them.
No, not at all. It sounds like magic.
Let's use an everyday example to explain what they thought was happening. The gloves in a box analogy.
Oh, that's a good one.
So let's say I take a pair of winter gloves. I put the left glove in a red box, and I put the right glove in a blue box. I mail the red box to you in New York, and I mail the blue box to someone in Tokyo.
Okay, a classic setup. I'm with you.
When you open your red box in New York and see a left glove, you instantly know with 100% certainty that the box in Tokyo contains a right glove.
Right, because they're a pair.
Exactly. There's no magic there. No spooky, faster-than-light communication happened between the boxes the exact moment you opened yours. The information was, well, it was already determined the moment I packed them.
Yes, what physicists call classical hidden information.
And initially, this is exactly what brilliant minds, including Einstein, believed quantum particles were doing. They thought the particles were just following a local hidden variable theory.
They assumed the particles were exactly like those gloves. They figured, the particles were carrying a hidden, pre-written set of instructions that dictated how they would behave when measured completely independently of each other once they separated.
Okay, let's unpack this, because this is where I get stuck.
Sure.
If you're a scientist looking at two particles behaving the same way, how could you possibly prove that they didn't have a secret, prearranged agreement before they were measured?
That's a great question.
How do you prove a negative? A hidden variable is, by definition, hidden.
It seems completely impossible, right? But what's fascinating here is the conceptual breakthrough that came from a physicist named John Bell.
Okay.
And based on a major review of his work by researcher Nicholas Brunner and his colleagues in Reviews of Modern Physics, Bell actually gave us the mathematical tools to test this.
Wait, mathematical tools to test hidden variables?
Yeah. Bell nonlocality. He realized that if the particles really were just like gloves with hidden instructions, there was a strict mathematical limit to how correlated their measurements could ever be over time.
Ah, okay. So it's sort of like a statistical speed limit for ordinary reality.
That's a great way to put it. A statistical speed limit. Bell proposed what we now call Bell inequalities.
Right.
He showed that if you measure the particles in very specific randomized ways, like changing the angle of your detectors at the very last microsecond, and you find that their correlations actually exceed this mathematical speed limit,
And what?
then it absolutely proves there was no pre-existing glove-in-a-box agreement. The particles have to be doing something fundamentally non-local. They aren't carrying a hidden script.
Okay, but math on a chalkboard is one thing. Actually catching particles in the act of communicating faster than light in a laboratory seems like a logistical nightmare.
Oh, it was a total nightmare. It took decades of relentless experimental work. The scientific community, they demanded what are known as loophole-free Bell tests.
Right, because if you're trying to prove quantum magic is real, you have to make sure the universe isn't just cheating the test somehow.
Exactly. And this was spearheaded by experimentalists like Elaine Aspect, John Clauser, and Anton Zeilinger. They actually won the 2022 Nobel Prize in Physics for this exact achievement.
Oh, wow. So how did scientists figure this out? Like, what were these loopholes they had to close?
Let's play this out. If you were testing this, how would you make absolutely sure the two measuring devices couldn't secretly coordinate their answers?
Well, I guess I'd move them really far apart. Like, put one across the room or across the city so that even a signal traveling at the speed of light wouldn't have time to reach the other one before the measurement was over.
Spot on. That is the locality loophole. You physically separate them so light speed communication is just impossible.
Okay, that makes sense.
But then the skeptics push back again. In early experiments, the photon detectors, well, they weren't great. They missed a lot of the particles.
Oh, I see where this is going.
Yeah. So skeptics argued, what if you're only detecting the photons that happen to agree with quantum mechanics, and you're just, missing all the ones that follow normal classical rules?
Oh, that's incredibly frustrating. The particles could just be hiding behind bad equipment.
Right. That's the fair sampling loophole, or the detection loophole.
So how did they fix that?
To close it, Clauser, Zeilinger, and their teams had to build incredibly highly efficient superconducting detectors to prove they were getting a truly representative sample of every particle passing through.
Okay, so they move them far apart,
Yeah.
and they made sure the cameras caught everything.
Yeah.
Does that cover it? What else could possibly go wrong?
The third one is, honestly, it's almost paranoid. It's the freedom of choice loophole.
Freedom of choice.
It asks, what if the universe somehow predetermined the settings on your measuring devices?
Wait, what?
Yeah. What if the particles, the detectors, and the scientists pressing the button all shared a common past event that orchestrated the whole experiment from the beginning?
Like a cosmic conspiracy. How do you even fight that?
By taking human choice out of it entirely. Scientists use insanely fast quantum random number generators to pick the measurement settings at the absolute last possible fraction of a nanosecond, while the particles were already in flight.
Wow, so the particles had absolutely no warning whatsoever.
None.
And when they closed all these loopholes, the locality, the fair sampling, the cosmic conspiracy, what happened?
The Bell inequalities were still violently shattered. The particles were genuinely entangled. Local realism was officially dead.
That is just a monumental shift. But,
Yeah.
proving entanglement is real just opened a new, weirder door. Because physicists then started asking, are all entangled particles equally connected?
Yes, and that led them into some wild theoretical territory.
Right. Which brings us to a famous review by the Horodecki Quartet, published in Reviews of Modern Physics 81, that kind of acts as the standard gateway to entanglement theory.
It's a foundational paper, absolutely.
They dive into the bizarre forms entanglement can take. And here's where it gets really interesting. They introduce this brilliant and, frankly, highly counterintuitive concept called bound entanglement.
Yes, bound entanglement. It's a tricky one.
Okay, let me see if I've got this right. The Horodeckis explain that you can use mathematical stress tests to identify entanglement.
Right?
There's one called the positive partial transpose, or PPT criterion. Basically, you take the math describing the particles, flip part of it backwards, and if the math breaks, you know they are entangled.
Correct. It's a very reliable diagnostic tool in quantum mechanics.
But they found that some entanglement passes that test, but is permanently trapped. It's undistillable, meaning via local operations, you can't extract it or purify it to use it for standard quantum computing tasks.
Exactly. And for a long time, physicists thought this bound entanglement was essentially just useless garbage, a dead end.
Like static on a TV.
Yeah. There was a famous idea called the Paris conjecture, which basically stated that if entanglement is bound and completely undistillable, it's simply too weak to ever violate a Bell inequality. It can't ever show that spooky non-locality.
But then researchers Thomas Vertesi and Nicholas Brunner completely disproved the Paris conjecture, didn't they?
They did. It was a massive shock.
They proved mathematically that even this junk, undistillable, bound, entangled state can still violate a Bell inequality, which is wild.
It is.
It's like having a digital lock that requires a highly specific, perfectly ordered code to open. And you have a code that is completely scrambled, totally corrupted. You can't extract a single readable word from it. Yet the sheer fact that the scrambled code exists somehow triggers the lock to open anyway.
That is a fantastic way to picture it. The scrambled code shouldn't be able to do the work, yet it
It's
does.
just magic.
It really showed us that entanglement, non-locality, and actual operational usefulness in a lab are three deeply distinct things. But all of this raises an important question.
Which is,
If entanglement is so powerful and it's happening all the time at this fundamental level, why don't we see it everywhere?
yeah, like why isn't my coffee cup entangled with my desk right now?
Physics has a very clear answer for this: decoherence.
Decoherence.
According to a major 2009 review by researcher Ken Furuya and his colleagues, decoherence is the ultimate enemy of entanglement. You see, entanglement is incredibly fragile.
How fragile are we talking?
Extremely. When a quantum system interacts with its environment, even if it's just a stray photon of sunlight or a single molecule of air bouncing off it, the environment essentially measures the system. And the moment it's measured, the quantum magic collapses.
Because the universe is a very messy place. It doesn't like keeping secrets.
It absolutely doesn't. Furuya's research focuses on how classical chaos and exponential instability drive something dramatically called entanglement sudden death.
Entanglement, sudden death. Okay, that sounds like a terrible heavy metal band.
It really does. But in quantum mechanics, it describes a very real, very frustrating scenario.
What exactly happens?
Due to local noise in the environment, the entanglement between particles doesn't just slowly fade away like a radio signal. It abruptly vanishes completely, flatlining to absolute zero before the system has even fully lost its quantum coherence.
Wait, it just snaps?
It just suddenly dies. Yes. And this fragility is the single biggest hurdle for anyone trying to build quantum technologies.
So what does this all mean? How are we overcoming that? Because we have this incredible universe-breaking phenomenon, but it's prone to sudden death the second a dust speck hits it. How is this actually impacting the listener's world today?
Well, we are learning to engineer highly isolated environments where entanglement can survive, and we are using it to trigger a technological revolution right now.
Like what?
Let's look at secure communications. There's a major focus right now on quantum key distribution, or QKD. Specifically, protocols like Eckert-91, named after physicist Arthur Eckert.
Okay, how does Eckert-91 actually work in practice?
It brilliantly uses those Bell inequality violations we talked about earlier. In normal encryption, if someone intercepts your password, they can copy it and you might never know.
Right, they just steal it quietly.
Exactly. But in Eckert-91, you send the cryptographic key using entangled photons. If a hacker tries to eavesdrop on the transmission, the physical act of them looking causes decoherence.
Because they become part of the environment. Their measurement suddenly kills the entanglement.
Exactly. And because the entanglement dies, the statistics of the Bell test completely change.
Oh, wow.
The sender and receiver instantly see that the mathematical speed limit is no longer being broken. It acts as an unbreakable, laws of physics-based alarm system. You will always know with absolute certainty if someone intercepted your message.
That is incredible. A physical burglar alarm made of math, and the ambition goes way beyond just sending passwords, right? According to a 2020 review in Nature Reviews Physics, there is a massive push toward building a full global quantum internet.
Yes, and to do this over vast distances without the signal dying from sudden death, scientists are using high-dimensional entanglement.
Meaning they're moving beyond just simple ones and zeros.
Much further beyond. Instead of just entangling the basic state of a photon, they are encoding data in complex, overlapping properties.
Like what kind of properties?
They entangle the photon's physical path, its orbital angular momentum, which is essentially twisting the light into a spiral, and they use time-frequency bins, slicing the photon's arrival time into incredibly tiny intervals.
That sounds impossibly dense.
It is. By stacking all these dimensions together, they can perform quantum teleportation and dense coding across satellite links and fiber networks. They are packing massive amounts of quantum information into these fragile connections.
And we can't forget about computing. Measurement-based quantum computing is a huge part of where this field is headed.
Oh, absolutely.
Most people think of a quantum computer like a traditional circuit board, just, faster. But this approach is completely different. You start with a massive, highly entangled web of particles called a cluster state.
Right.
Think of it like a giant block of pristine, entangled marble. To run your algorithm, you don't build up a calculation step by step.
Yeah.
You actually just make local measurements on specific particles.
Which destroys the entanglement.
Exactly. Every measurement destroys a little piece of the entanglement, effectively chiseling away at the marble block. And the physical state that is left behind at the end of the chiseling, well, that is the answer to your calculation.
I love that analogy. It completely flips the paradigm of computation. You're computing by destroying entanglement in a highly choreographed way.
It's beautiful.
And these applications even extend to how we measure the universe itself. The field of quantum metrology uses entangled states to surpass the fundamental limits of classical measurement.
How so? What limits are we bypassing?
Well, normally, light behaves a bit like a stream of random particles, which creates a fuzzy background static called shot noise. It's like trying to listen to a whisper in a really crowded room.
Okay, I can picture that. Just annoying static.
But by entangling the photons, we coordinate their behavior. We force them to jitter together, effectively canceling out that random static. This achieves what's called sub-shot noise precision.
So the whisper becomes crystal clear.
Exactly. This is the exact technology being developed right now to detect the faintest microscopic ripples in gravitational waves, or to build ultra-precise atomic clocks that wouldn't lose a single second, even if they ran over the entire age of the universe.
That is just staggering. We are manipulating the universe's source code to build better clocks and an unbreakable internet.
We really are.
But as amazing as all that technology is, this deep dive takes one final, massive turn. So we've talked about pairs of particles, maybe a network of photons. But scientists are now realizing that entanglement scales up to the size of the universe itself.
If we connect this to the bigger picture, this is where things get truly profound. We have to look at the 2008 review by physicists Jens Eisert, Marcus Kramer, and Martin Plenio on something called area laws.
Okay, area laws. Break that down for us.
Now think about classical physics. If you want to know the total entropy, the total amount of disorder, or the total information capacity, in a physical volume, say the room you're sitting in right now, it scales with the volume of that room. A bigger 3D room means more space for more stuff.
Makes perfect sense. If I double the size of my room, I can fit double the amount of furniture and air molecules.
But in quantum many-body systems, systems with massive amounts of interacting entangled particles, the entanglement entropy of a region doesn't scale with its 3D volume.
Wait, it doesn't?
No, it scales with its 2D boundary area.
Wait, let me make sure I'm really getting this. Look around the room you're in right now. Classical physics says the amount of stuff or information in that room depends on the volume. But quantum mechanics suggests that all the information describing your room, your furniture, and your unentangled coffee cup could mathematically be encoded entirely on the two-dimensional paint of the walls surrounding you.
That is exactly what it's saying. The 3D space is an illusion created by the 2D boundary, and the implications of this are just earth-shattering.
I mean, my mind is already blown.
Because where else in the universe do we see an area law? In black hole thermodynamics, Stephen Hawking and Jacob Bekenstein discovered decades ago that the information content of a black hole isn't proportional to its massive internal volume. It's entirely proportional to the surface area of its event horizon.
So the mathematics of microscopic quantum entanglement perfectly match the mathematics of the most massive objects in the universe.
Yes. And it gets deeper. This long-range entanglement gives rise to what physicists call topological order.
Which is what exactly?
It's something we observe in exotic states of matter, like fractional quantum Hall states, where electrons completely reorganize themselves based on entanglement geometry rather than normal classical forces.
But how does this connect to actual spacetime, like the fabric of reality?
Through the study of quantum gravity, researchers are using highly advanced mathematical bridges, specifically the Ryu-Takanagi formula and the AD-SCFT duality.
Okay, let's slow down. Walk me through the AD-SCFT duality.
Sure. Imagine a snow globe.
Okay.
The AD-SAP part anti-de Sitter space is the 3D volume inside the glass. That's the bulk where gravity exists.
Got it. The water and the little house inside.
Exactly. Now, the CFT part conformal field theory is the 2D glass surface itself, where quantum particles interact without gravity.
Okay, so 3D inside, 2D outside.
What the Ryu-Takanagi formula proved is that the amount of quantum entanglement happening on the 2D glass surface perfectly calculates the exact geometry of the 3D space inside.
I need a second to process that.
Yeah.
You're saying the geometry inside the snow globe is physically generated by the entanglement happening on the outside glass.
Exactly.
Yeah.
Researchers in the frontiers of quantum gravity are realizing that space-time geometry itself might not be a fundamental empty backdrop of the universe. Space and time might actually emerge from the structure of quantum entanglement.
So space and time aren't just an empty stage where particles do their thing. Space and time are a quilt. and they are literally stitched together by the invisible threads of quantum entanglement.
That's beautifully put.
Without entanglement connecting everything, distance itself might not even exist.
That is the bleeding edge of modern theoretical physics. Entanglement isn't just something happening in reality. Entanglement is the glue of reality.
Unbelievable.
Mm.
Well, we have covered an enormous amount of ground today on this deep dive. Let's summarize the key takeaways for you listening right now. First, entanglement fundamentally disproves local realism. The spooky action is real, it's not a hidden trick, and it has been verified beyond a shadow of a doubt by loophole-free Bell tests. Second, while this entanglement is incredibly fragile and highly susceptible to sudden death from decoherence, scientists are successfully manipulating it right now to build unhackable quantum networks and impossibly precise tools to measure gravitational waves.
It's amazing technology.
And third, entanglement isn't just a quirk of tiny particles. It governs the hidden rules of quantum many-body systems and is very likely the underlying mechanism that projects the geometry of space-time itself.
It is a beautiful scientific trajectory. We've watched science transform entanglement from a philosophical headache that deeply bothered Albert Einstein into a quantifiable operational resource.
Like coal or electricity.
Exactly. Something we can measure, test, and use, just like energy or information.
It really is a triumph of human curiosity, and it leaves me with one final, slightly terrifying, but totally fascinating thought to leave you with.
Oh, I'm ready.
If the three-dimensional space we walk around in, our entire physical reality, your room, your town, your planet, is actually just an emergent illusion projected from the boundary of an area law, what happens to our reality if the entanglement holding our universe together experiences entanglement sudden death?
Wow. A haunting and phenomenal question to end on.
Something to ponder while you drink your securely unentangled coffee. Thank you for joining Deep Dive Lab, and don't forget to follow and subscribe for more science stories where we decode the mysteries of the universe.